Hello all, I am Sudarsun. I am an assistant professor at Rutgers University. I'll be presenting our work, MicroMon, which is a monitoring framework for tackling geo-distributed heterogeneity. This is a joint work with my past students Babar Khalid, Nolan Rudolph, and Professor Durairajan at University of Oregon. As we all know, modern data centers are increasingly becoming geo-distributed. Applications like Cassandra and Apache Spark are getting deployed across multiple data centers. Geo-distributed data centers generally contain heterogeneous hardware, which also includes storage level heterogeneity as well as wide area network heterogeneity in terms of fiber optics and InfiniBand. Hardware heterogeneity in data centers generally avoids vendor lockout and reduces operational cost by combining older, cheaper, and probably slower with newer, expensive, and faster hardware. Hence, careful provisioning of applications can provide higher performance at lower cost. Unfortunately, current monitoring frameworks for geo-distributed applications are unidimensional. For example, they only consider the host level information or storage device information or network level information in isolation. In general, they lack heterogeneity awareness. For example, there is no aware of different types of storage hardware and could impact IO-intensive applications. The other problem is that most of these systems are coarse-grained, which means they're unaware of host-level micrometrics in software and hardware. These micrometrics could include even end-host information such as how much page cache is this application using, or the node-level IO traffic, or a node's network queue delays. To overcome these challenges, we propose MicroMon, which is a fine-grained monitoring and dissemination and inference framework. MicroMon collects fine-grained software and hardware micrometrics in the end host. We call them micrometrics because these include smaller software and hardware metrics such as, say, page cache utilization or disk read and write across each host in a large distributed data center. Further, MicroMon can also filter micrometrics into anomalies to efficiently disseminate these information. It enables replica selection for geo-distributed applications such as Cassandra. And our preliminary study of MicroMon integrated with Cassandra shows that by enabling heterogeneity awareness, MicroMon can significantly improve Cassandra's performance in terms of throughput gains. So in the next part of my talk, I'm going to take one case study that is Cassandra. However, the principles of MicroMon are generic across multiple applications. Cassandra is a distributed NoSQL database system deployed across geographically distributed data center. It manages large amount of structured data in commodity servers. It provides highly available service and doesn't have a single point of failure and focuses mainly on availability and partition tolerance. Cassandra is considered to be used widely across multiple organizations. It follows its predecessors like GFS and Dynamo by enabling replication. Anytime a request comes in from the client, it uses consistent hashing to route the request. The request is then sent to a server, which then replicates across the workers. Cassandra also provides rack awareness, which means it can split requests, replica requests to multiple racks, such a way that even if one rack fails, it could recover the data. Further, it also provides data center level awareness, which means that the data could be replicated across multiple data centers. Given the geographically distributed nature of Cassandra, it also needs to monitor network topology and route requests, for which it uses a mechanism called Snitch. Snitch monitors read latencies and avoids non-responsive replicas. There are different types of snitching, for example, gossip, multi-region snitch. For example, the gossip snitch uses rack and data center information to send or gossip across nodes and collect latency information. However, one problem with this monitoring mechanism is that it lacks hardware heterogeneity awareness. It only considers network latency, but fails to consider other resources such as storage. To understand this problem and highlight this problem, we consider a very simple experiment where a set of nodes are used using a set of nodes use SSD replica, and other set of replica nodes uses hard disk. Clearly, the nodes using SSD replicas have higher I/O throughput. For simplicity, we assume the network latency across SSD and HDD replica to be the same for this analysis. And we use well-known and widely used YCSD benchmark, which is with workload A, B, and C configurations with different read and write ratios for the benchmark. To understand the impact of storage heterogeneity awareness, on the x-axis is different workloads and the y-axis is operation in terms of throughputs per operations per second. First, with HDD only configuration, we force Cassandra to route requests to only replicas with hard disk. Then we route request to nodes with only SSD, which shows a significant performance gain, and this can be considered as an optimal performance. Next, Cassandra also has a snitching mechanism which dynamically monitors the network latency, but it fails to consider the storage heterogeneity. So as you can clearly see, the throughput significantly reduces compared to the optimal SSD only case. This motivates a need of heterogeneity awareness. To overcome these problems, we designed MicroMon, which is a monitoring and inference framework for geo-distributed applications. MicroMon performs fine-grained micrometric monitorings at both software and hardware. These micrometrics include such as information like page cache or hardware characteristics of an end host, and also network level micrometrics. MicroMon efficiently disseminates the collected micrometrics. Our ongoing work is looking at how to inference these collected micrometrics at an inference engine, which could be a distributed node. Now, collecting fine-grained micrometrics has several challenges. The first question is the selection problem. It says what micrometrics should we consider? The second problem is how to efficiently disseminate the collected micrometrics. And the third problem is how to quickly infer from these micrometrics and make a decision about, say, where do we route the request to. So with the selection problem, unfortunately, there can be huge combination of micrometrics across apps, host OS, network, and so on. And these micrometrics across could vary depending on application perceived metrics. For example, an application that is latency sensitive could have different micrometrics compared to an application that is throughput sensitive. So our approach is simpler. We start with just storage and network micrometrics. And more importantly, to identify the relevant hardware and software micrometrics, we use the resource usage as a proximity. For example, an application using high storage usage, we monitor the page cache and hardware read and write latency. So at a high level, given an enterprise setting where there are multiple data centers connected by an enterprise backbone, we collect storage level micrometrics. We also collect network level micrometrics, which is end host network micrometrics. And finally, we also connect micrometrics at the switch level. One problem is that there could be huge amount of micrometrics that needs to be disseminated. Now, let's take a simple example of an SSD in a single node. Modern SSDs provide smart counters, and there could be up to 32 smart counters even for a single node. Now, disseminating this information across thousands of nodes has high overhead, and the cost would increase with the hardware and software components. One observation, however, we make is that the OS has already directly or indirectly exposed some of these anomalies. For example, if an application is suffering from high I/O wait time, we can infer that the application has high page cache misses. Similarly, if an application is using sustained bandwidth, its sustained bandwidth is lower than the max hardware bandwidth, then we know that the application has issues with the storage hardware. Similarly, the network I/O queue wait time in the OS alludes to TCP congestion. So the brief idea is that instead of sending thousands of micrometrics across decision agents, we only report OS perceived anomalies. Now, the next question is how frequently should we send anomalies to the inference engine? And what is the best mechanism to send them? Unfortunately, there is not good mechanism to send these information, but we take an observation that modern enterprise systems have network telemetry, which offers aggregated stats about the state of the network. Therefore, we propose co-designing this network telemetry, for example, in-band network telemetry, to not only connect network level information, but also connect host level information. A typical packet collected through in-band telemetry with our proposed scheme would look like an int header with network anomalies and int payload with the end host anomalies. Of course, these anomalies need to be pre-established with some form of threshold, which is an ongoing work in our current work. Once these anomalies are collected, we also need to infer and make a decision. Current mechanisms like Cassandra make simple decision making. For example, they sort all the network latencies and then they replicate this. Then they choose a replica based on the network latency. However, one problem is that for bandwidth sensitive applications, we need higher weights for WAN-based micrometrics compared to host level micrometrics. Similarly, we could imagine several different cases. So at a high level, one approach is that instead of only looking at like network level information, we look at equal weights for all software and hardware micrometric. We use collected micrometrics to calculate a replica score, and then we route requests to replicas with higher score. We also provide flexibility to assign higher weights for WAN-based network micrometrics. Let's assume that if an application demands higher bandwidth. However, our proposed mechanism is currently simple, and we need a more generic and self-adaptive inference engine that can automatically translate application level metrics to a set of micrometrics, which is a scope of our ongoing work. To understand this initial realization of MicroMon, we conduct experiment by understanding how well can MicroMon adapt to storage heterogeneity. Can it adapt to a combination of storage heterogeneity plus network latency? And also what happens if we include other fine-grained micrometrics, for example, page cache, and you can look for these details in the paper. For our analysis, we use a multi-cloud infrastructure where replicas are located at 3 different data centers, Utah, APT, and Emulab. The Utah replicas generally have NVMEs. The APT replicas have HDDs. And the Emulabs have the master node, which also has HDDs. The network latency between Utah and the master node is slightly higher, although their disks are faster. Similarly, the network latency between APT replica and master node is around 400 microseconds. Again, for all our experimentation, we use YCSB benchmark with workload A, B, and C configuration with varying read and write counts. So first, to understand if MicroMon can adapt to storage heterogeneity in Cassandra, on the x-axis shows different workloads with different client configurations. So 32 clients means there are 32 clients that are simultaneously making requests. On the y-axis shows the throughput in terms of operations per second. First, with HDD only configuration, we artificially force application to send all the requests to replicas in HDD node. Again, with SSD, it's the optimal case where all the requests are routed to an SSD node. Finally, we also use Snitch, which is unaware of the hardware heterogeneity, specifically the storage heterogeneity, as a result performs poorly. In contrast, MicroMon, by ensuring that it not only considers network aspects, but also storage aspects, is able to balance the request in ways that it can achieve maximum performance. In fact, our performance shows that for increasing number of client threads, the performance improves by up to 49%. Next, to understand the multidimensional capability of MicroMon, we also include network latency, which means for the SSD replicas, we also increase the number of the network latency from 0 milliseconds to 25 milliseconds. The y-axis shows the throughput. As you can see, compared to Snitch, MicroMon provides significant performance benefits until the latency is around 5 milliseconds. Even beyond that, MicroMon is able to provide sustained performance. So this shows the adaptable capability of MicroMon. To conclude, data center systems are becoming more and more heterogeneous. Deploying geo-distributed applications in heterogeneous data centers requires redesign of monitoring mechanisms. We propose MicroMon, a fine-grained micrometric monitoring, dissemination, and inference framework. Our ongoing work will focus on how to efficiently disseminate and provide self-adaptive inference mechanisms. With this, I'm happy to take questions online or offline. Thank you.